Good day, everyone. Welcome to our session for today. So, this time, class, we're going to discuss the introduction to advanced statistics. Okay, so this lecture material class is based on the lecture materials done by Professor Joy V. Lorin Picar in Davao del Norte State College, New Visayas, Panabo City. Okay, so we're so thankful that we have this material. I saw it very useful, no, in our for our class. Okay, so these are the topic outlines. So part one, uh, role of statistics in research. We have about descriptive statistics, hands-on on statistical software, sample and population, sampling procedures, sampling size, hands-on statistical software, inferential statistics, hypothesis testing, hands-on statistical software. And part two will be the choice of statistical tests, defining independent and dependent variables. And once again, we have here the hands-on statistical software. So scale of measurements, how many samples, groups are in the design. Then part three, we have the parametric tests, hands-on statistical software. In part 4, we have non-parametric tests, and then we have the hands-on statistical software. Part 5 will be about goodness of fit, and we also have the hands-on statistical software. Part 6, we have choosing the correct statistical tests, then hands-on statistical software, introduction to multiple and nonlinear regression. And then we have hands-on statistical software. So for this part class on hands-on statistical software, so this is the thing that I want you to do it yourself. No, you just find those statistical software that you can use in our study now for your project now that I'm going to mention later. So here's the rule of the statistics in research. So normally statistics used to analyze data, no? To organize and make sense out of large amount of data. So this basic to intelligent reading research article. So this is basic, no? This is basic to intelligent reading research article. So significant contributions in social sciences, no? Statistics. Statistics in research has significant contribution in social sciences, applied sciences, and even business and economics. Statistical researches make inferences about population characteristics on the basis of one or more samples that have been studied. So, how is statistics look into? So, we have two or three items here: the descriptive, correlational, and inferential. So, when we speak of descriptive, so this gives us information or simply describe the sample we are studying. Then for the correlational, so this enables us to relate variables and establish relationship between and among variables which are useful in making predictions. So we have some mathematical calculations that we're going to explore, no, after this introductory part. Then inferential statistics, this is going beyond the sample and make inference on the population. So we have also some details of this part later on. So for the descriptive statistics, so we have here an example. No? We have n, the number total population size or sample size from any given population. So example of population, something like this class. So minutes spent on the phone. Okay, so here are the data, how many minutes people use or spend using their phone. So that's just an example. Then for those information class, for those sample population, we can calculate the range, mean, median, and mode. So when we speak of mean, median, mode, and range, so these terms describe the properties of statistical distributions. And in statistics, a distribution is the set of all possible values for terms that represent defined events. So the value of a term when expressed as a variable is called a random variable. And there are two major types of statistical distributions. The first type has the discrete random variable. This means that every term has a precise isolated numerical value. An example of a distribution with a discrete random variable is the set of results for a test taken by a class in school. Then the second major type of distribution has a continuous random variable. So in this situation, a term can acquire any value within unbroken, an unbroken interval or span. Such a distribution is called a probability density function. So this is the sort of function that might, for example, be used by a computer in an attempt to forecast the path of a weather system. Okay, so these are the uh, very important concept class about this discrete random variable and continuous random variable. And to give us details on the first item, the mean. So the most common expression of the mean of statistical distribution with a discrete random variable is the mathematical average. Okay, so this is a mathematical average of all the terms. So to calculate it, what we are going to do, just add up the values of all terms and then divide by the number of terms. So we will get the mean. So this expression is also called the arithmetic mean. Okay, so mean or arithmetic mean, just the same thing. So there are other expressions for the mean of a finite set of terms, but these forms are rarely used in statistics. So the mean of a statistical distribution with a continuous random variable, also called the expected value. Okay, so take note on this. The mean of a statistical distribution with a continuous random variable is also called expected value. And this is obtained by integrating the product of the variable with its probability as defined by the distribution. So the expected value is denoted by the lowercase letter mu. Okay, so this is letter mu. So that is our expected value or continuous random variable. Then next we have the median. So median of distribution with discrete random variable depends on whether the number of terms in the distribution is even or odd. If the number of terms is odd, then the median is the value of the term in the middle. Okay, so you should know how to differentiate the mean, median. When we speak of median, so this is a discrete random variable. Depends on whether the number of terms is in the distribution is even or odd. So if the number of terms is odd, then the median is the value of the term in the middle. Okay, so if for example we have 1 2 3 4 5, so there are 5 items, so the median would be the third number. Okay, so that's the median. So this is the value such that the number of terms having value greater than or equal to it is the same as the number of terms having values less than or equal to it. If the number of terms is even, then the median is the average of the two terms in the middle. You just find the middle terms, you add them, and you divide it by 2, then that would be the median. So such number of terms having values greater than or equal to it is the same as the number of terms having values less than or equal to it. So the median of a distribution with a continuous random variable is the value m such that the probability is at least 1/2 or 50% that a randomly chosen point on the function will be less than or equal to m. And the probability is that at least one half that a randomly chosen point on the function will be greater than or equal to m. Okay, so that's the concept about median. And then we have mode. So the mode of a distribution with a discrete random variable is the value of the term that occurs the most often. Okay, so whatever is the value that appears several times, the most, no, the most. So that will be the mode. So it is not uncommon for a distribution with a discrete random variable to have more than one mode, especially if there are not many terms. So this happens when two or more terms occur with equal frequency and more often than any of the others. So a distribution with two modes is called bimodal. Okay, so there are times that this situation will also happen. So we call that two modes as a bimodal. A distribution with three modes is called trimodal, and the mode of distribution with a continuous random variable is the maximum value of the function. So as with discrete distribution, there may be more than one mode. Okay, so as with discrete distributions, there may be more than one mode. Then we have what we call range. So the range of a distribution with a discrete random variable is the difference between the maximum value and the minimum value, meaning the highest value minus the lowest value. So that will be the range. So for a distribution with a continuous random variable, the range is the difference between the two extreme points on the distribution curve where the value of the function falls to 0. So for any value outside the range of a distribution, the value of the function is equal to 0. So the least reliable of the measure and is used only when one is in a hurry to get a measure of variability. Okay, so this is the least, no, the range, the least reliable of the measure and is used only when one is in a hurry to get a measure of variability. Okay, so we have what we call variance. So we have standard deviation and variance. The variance and closely related standard deviation are measures of how spread out a distribution is. In other words, they are measure of variability. So the variance is computed as the average square deviation of its number from its mean. So for example, for the number 1, 2, 3, the mean is 2. And the variance is, this is the calculation of variance. So 1 minus 2 plus 2 minus 2 plus 3 minus 2. Then there are three numbers, three items here. You divide by 3 equal to 0.667. Okay, you just square the variance, you add them, then divide by the number of items. Okay, so the formula in the summation notation for the variance is in a population is given by this. So variance is equal to the summation of x minus mu divided by n. So x minus mu, the quantity here is being squared, divided by n. So we get the square, no? Square of the variance. Okay, so where mu is the mean and n is the number of scores. So when the variance is computed in a sample statistic. So variance, we have what we call S equal to summation of x, quantity x minus m divided by n, where m is the mean of the sample and can be used. So m is the mean of the sample, can be used. So S squared is a bias, no? A biased estimate of the variance squared. However, By far, the most common formula for computing the variance in a sample is given by this equation below. S squared equal to the summation of the difference, the square of the difference of x and m divided by n minus 1, which gives an unbiased estimate of the variance, squared variance. Since samples are usually used to estimate parameters, S squared is the most commonly used measure of variance. So calculating the variance is an important part of many statistical applications and analysis. It is the first step in calculating the standard deviation. So what is a standard deviation? Standard deviation formula is very simple. It is the square root of the variance. So you have the formula of variance, or we have sigma squared, then equal to something on the right side. You take square root on both sides, then you will be able to get the standard deviation. So an important attribute of the standard deviation as a measure of spread is that if the mean and standard deviation of a normal distribution are known, it is possible to compute the percentile rank associated with any given score. Okay, so in a normal distribution, about 68% of the scores are within one standard deviation of the mean, and about 95% of the scores are within the two standard deviations of the mean. So the standard deviation has proven to be an extremely useful measure of spread, in part because it is mathematically tractable, and many formulas in the inferential statistics use the standard deviation. And we have what we call coefficient of variation. So what does coefficient of variation, or we have CV? So what does it mean? Coefficient of variation. So CV, or coefficient of variation, is a statistical measure of the dispersion of data points in a data series around the mean. It is calculated as follows: coefficient of variation equal to standard deviation divided by the expected return. So the coefficient of variation represents the ratio of the standard deviation to the mean, and it is a useful statistic for comparing the degree of variation from one data series to another, even if the means are drastically different from each other. Then we have here the coefficient of variation. So the coefficient of variation will be calculated using this formula. So this is a statistical measure of dispersion of data points in a data series around the mean. So it is calculated as follows: coefficient of variation, we have the standard deviation divided by expected return. So the coefficient of variation represents the ratio of the standard deviation to the mean, and it is a useful statistic for comparing the degree of variation from one data series to another, even if the means are drastically different from each other. So we still have to compare it in this manner using this formula for coefficient of variation. Then we have kurtosis. So what does kurtosis mean? So this is a statistical measure used to describe the distribution of observed data around the mean. So it is sometimes referred to as the volatility of volatility. So the kurtosis or axis measures the relative flatness of a distribution as compared to the normal distribution, which shows kurtosis of 0. So positive kurtosis indicates tapering distribution, also called leptocortic distribution, whereas the negative kurtosis indicates flat distribution, or we call it platycortic distribution. So the kurtosis is defined by the following formula. So g sub 2 equal to mu sub 4 divided by s to the fourth power minus 3, or equal to the 1 over n summation of times the summation of x sub I minus x bar divided by s. So this part here, this ratio, x, the quantity xi minus x bar divided by s raised to power 4. So minus 3, no, the whole thing here, minus 3. So this equation of the kurtosis is valid for a sample and is a biased estimator. So biased estimator of the kurtosis of the population. In order to estimate the kurtosis of the population, you have to use the following formula. Okay, so this is the formula, class. G2 is equal to, okay, we have this part here, n times n plus 1 divided by the quantity n minus 1 times n minus 2 times n minus 3 times the summation of the x sub j minus x bar divided by s, and this whole thing here raised to power 4, where we have here from j equal to 1 to n, and the whole thing is minus or subtracted with this quantity here, or this part here, 3 times n minus 1 squared divided by n, the quantity n minus 2 times n minus 3. So below here, you find two examples of examples of distributions with different kurtoses. Okay, so you see here the appearance, no, of the distribution with kurtosis equal to minus 0.616. So this is what we call platykortic curve, and we have here the leptokortic with a kurtosis of 0.810. Okay, so note that the kurtosis is sometimes defined by another formula, omitting the term negative 3. Negative 3 in the formula above here. In this case, a normal distribution would yield a kurtosis of 3. Okay, so the result will be a distribution with a kurtosis of 3. So another example here. So examples, the following example shows histogram for 10,000 random numbers of generated form, or sorry, the following example shows histograms for 10,000 random numbers generated from a normal, a double exponential, a Cauchy, and a Weibull distribution. Okay, so we have here random numbers. So skewness here is 0.03 and kurtosis of 2.962. Okay, and then we have a double exponential random numbers, skewness of 0.062 and kurtosis of 5.903. Weibull gamma equal 1 to 1.5 random numbers. Okay, so we have here for Cauchy random numbers. So we have here the skewness, no? 69.9, kurtosis of 6.693. And here for the Weibull gamma, so Weibull, the gamma equal to 1.5 random numbers. So the skewness here is equal to 1.082 and the kurtosis is equal to 4.46. So these are the examples of the kurtosis, the graph showing the kurtosis. So when you speak of kurtosis, the details of this, kurtosis refers to how sharply picked a distribution is. How sharply peaked distribution is. So a value for kurtosis is included with a graphical summary. So values close to 0 indicate normally peaked data. The negative values indicate a distribution that is flatter than normal. Then for the positive value or positive values indicate a distribution with a sharper than normal peak. Okay, as you can see in this picture. Okay, so for example, this one. So we have this graph. So the distribution is flatter than normal and has a kurtosis value of 1.253. Okay, so flatter than normal. Then we have here distribution more than sharply peaked than normal and has a kurtosis value of 3.804. All right. Then we have what we call skewness. So what does it mean, skewness? Skewness and kurtosis, now as illustrated in these pictures here, we have seen here the skewness and kurtosis. So in the graph class, this is usually indicated now, determine the skewness and also the kurtosis. So skewness and kurtosis, a fundamental task in many statistical analysis is to characterize the location and the variability of a data set. So further characterization of the data includes skewness and kurtosis. So skewness is a measure of symmetry, or more precisely, the lack of symmetry. A distribution or dataset is symmetric if it looks the same to the left and right of the center point. So the histogram is an effective graphical technique for showing both the skewness and kurtosis of dataset. So here's the definition of skewness. For the univariate data, we have y1, y2, and so on and so forth until yn. So the formula for skewness is given by the summation of y minus y bar, uh, this one raised to power n, divided by n minus 1 raised to power n cubed, where this part here is the mean. So this is S, sorry class, this is S now, raised to power S. So this is S. And this one is what we call standard deviation, and N is the number of data points. The skewness of a normal distribution is 0. For normal distribution is 0, so it didn't skew to the right or left. So normal distribution skewness is equal to 0. And any symmetric data should have a skewness near 0. So negative value for the skewness indicates that data that are skewed left. For the negative data are skewed left, and positive value for the skewness indicate that data are skewed right. So by skewed left, we mean that the left tail is long relative to the right tail. It's something like this one. Okay, so if you have something like this, skewed to the left. If you have something like this, skewed to the right. Okay, so some measurements have a lower bound and are skewed right. For example, in our reliability studies, failure times cannot be negative. So samples and population. Population, as used in research, refers to all members of a particular group. It is the group of interest to the researcher. So this is the group of whom the researcher would like to generalize the result of a study. Okay, so that's what we call samples and populations. So a target population is the actual population to whom the researcher would like to generalize. Accessible population is the population to whom the researcher is entitled to generalize. So you have to remember these terms also, class. Then we have what we call sampling. So this is the process of selecting the individuals who will participate in a research study. Any part of the population of individuals of whom information is obtained. Alright, then a representative sample is a sample that is similar to the population to whom the researcher is entitled to generalize. Then we have what we call probability and non-probability sampling. So a sampling procedure that gives every element of the population or a known non-zero chance of being selected is the sum in the sample is called probability sampling. Otherwise, the sampling procedure is called non-probability sampling. So whenever possible, probability sampling is used because there's no objective way of assessing the reliability of inferences under non-zero probability sampling. So here are the methods of probability sampling. One, simple random sampling. We have systematic sampling. We have stratified sampling, cluster sampling, two-stage random sampling. So these are the methods of probability sampling. So here's the details of each item here. So simple random sampling, this is a sample selected from a population in such a manner that all members of the population have an equal chance of being selected. Alright, then for the stratified random sampling, sample selected so that certain characteristics are represented in the sample in the same proportion as they occur in the population. Now for the cluster random sample, this is obtained by using groups as the sampling unit rather than individuals. So I'll show you examples on this different sampling class later on. So two-stage random sample selects group randomly and then chooses individuals randomly from these groups. Then for the non-probability sampling, we have what we call accidental or convenience sampling. We have purposive sampling, quota sampling, snowball or referral sampling, and systematic sampling. So for the systematic sample, so this is obtained by selecting every nth name in a population. Then for convenience sampling, this is obtained by selecting for convenience sampling, any group of individuals that is conveniently available to be studied. So that is what we call convenience sampling. Purposive sampling consists of individuals who have special qualifications of some sort or are deemed representative on the basis of prior evidence. Then quota sampling. In quota sampling, the population is first segmented into mutually exclusive subgroups. Just as in stratified sampling, then judgment is used to select the subjects or units from each segment based on a specified proportion. And for example, an interviewer may be told to sample 200 females and 300 males between age of 45 and 60. This means that individuals can put a demand on who they want to sample or target. So that is an example of targeting. No? Snowball sampling. Snowball sampling is a technique for developing a research sample where existing study subjects recruit future subjects from among their acquaintances. Thus, the sample group appears to grow like a rolling snowball. As the sample builds up, enough data is gathered to be useful for research. The sampling technique is often used in hidden populations, which are difficult for researchers to access. Example populations would be drug users or prostitutes. Sample members are not selected from sampling frame. Snowball samples are subject to numerous biases. We have here the general classification of collecting data. So census or complete enumeration is the process of gathering information from every unit in the population. So not always possible to get timely, accurate, and economical data. So there are a lot of reasons why we cannot do it that way. So costly if the number of units in the population is too large. Then the second one is some survey sampling. It's a process of obtaining information from the units in the selected sample. So the advantages, it reduces cost, greater speed, greater scope, and greater accuracy. So for the sample size, samples should be as large as a researcher can obtain with a reasonable expenditure of time and energy. As suggested, a minimum number of subjects is 100 for a descriptive study, 50 for a correlational study, and 30 in each group for experimental and causal comparative design. So according to Padua, for n parameters, minimum n could be computed as n greater than or equal to p plus 3 times p over 2, where p is the parameters. Say if p is equal to 4, thus minimum n equal to 14. We have here our n is p plus 3 quantity, p plus 3 times p over 2. So where p is the parameters. So in this case, for p is equal to 4, so this is 4, so 7, 7, we have 7, 7 times, we have, if this is 4, 4 plus 3, 7, okay, then 4 divided by 2 is 2, 2 times 7, p is equal to 14, sorry, n is equal to 14. So our n must be greater than or equal to the result, no, when you substitute the value of p here. So the requirement is that n must be greater than or equal to this, the quantity p plus 3 times p divided by 2. So in this case, when p is equal to 4, so substitute p here, which is 4, 4 plus 3, 7. This is 4 divided by 2, 2, 2 times 7 equal to 14. So our n is equal to 14. Then we have what we call inferential statistics. This is 40 formalized techniques used to make conclusion about population based on samples taken from the population. Then next we have hypothesis. So what is this hypothesis? Hypothesis is defined as the tentative theory or supposition provisionally adapted to explain certain facts and to guide in the investigation of others. A statistical hypothesis is an assertion or statement that may or may not be true concerning one or more population. For example, a leading drug in the treatment of hypertension has an advertised therapeutic success rate of 83%. A medical researcher believes he has found a new drug for treating hypertensive patients that has higher therapeutic success rate than the leading drug with fewer side effects. So we have to eliminate this class. Rate than the leading. So we have to eliminate this. Okay, so rate than the leading drug with fewer side effect. So the statistical hypothesis, we have here h sub o or h sub 0. So you can have this as your hypothesis. The new drug is no better than the old one. P equal to 0.83. So that is our hypothesis. Then we have here H1, H sub 1. The new drug is better than the old one. So P greater than 0.83. Okay, so this is how to formulate your hypothesis. Example 2. By the way, this one is based on this example here. Okay. So the other one, we have a social researcher is conducting a study to determine if the level of women's participation in community extension program of the barangay can be affected by their educational attainment, occupation, income, civil status, and age. Okay, so we can have here the hypothesis. At Sabo, the level of women's participation in community extension program is not affected by their attainment, occupation, income, civil status, and age. So at sub 1, the level of women's participation in community extension program is affected by their attainment, occupation, income, civil status, and age. Okay, so that's how to formulate a hypothesis. So we'll have the uh, null hypothesis and alternative hypothesis, which I'm going to explain later. So example 3, a community organizer wants to compare the three community organizing strategies applied to cultural minorities in terms of effectiveness. Okay, so we have here you can practice this class now. How will you uh, create or formulate your hypothesis out of this scenario? Now, hypothesis testing. So steps in hypothesis testing. 1. Formulate the null hypothesis and the alternative hypothesis. So this is the statistical hypothesis, which are assumptions or guesses about the population involved. In short, these are statements about the probability distribution of the population. So null hypothesis. So what is this? This is a hypothesis of no effect. So it means that it usually formulated for the express purpose of being rejected. Okay, so for being rejected, that is, it is the negation of the point one is trying to make. Okay, then this is the hypothesis that two or more variables are not related, or that two or more statistics are not significantly different. So that's for the null hypothesis. For the alternative hypothesis, this is the operational statement of the researcher's hypothesis. The hypothesis derived from the theory of the investigator and generally state a specified relationship between two or more variables, or that two or more statistics significantly differ. Alright? And two ways of stating the alternative hypothesis. One is predictive, the other one is non-predictive. So for predictive, it specifies the type of relationship existing between two or more variables, direct or indirect, or specifies the direction of the difference between two or more statistics. Now for the non-predictive, it does not specify the type of relationship or the direction of the difference. And we have here what we call level of significance. We denote this by the symbol alpha. So level of significance alpha is the maximum probability with which we would be willing to risk type 1 error. The hypothesis can be inappropriately rejected. The error of rejecting a null hypothesis when it is actually true. Plainly speaking, it occurs when we are observing a difference difference when in truth there is none, thus indicating a test of poor specificity. An example of this would be if a test shows that a woman is pregnant when in reality she is not. Alright, so we have a detailed explanation of this class later on for more details of this part. In other words, the level of significance determines the risk a researcher would be willing to take in his test. So the choice of alpha is primarily dependent on the practical application of the result of the study. For example, we have here an alpha of, say, 0.05. So it means 95% confident of the claim. Okay, or if you have 0.01, so it means that 99% confident of the claim. Sorry, 99% that the claim or the researcher's claim is confident that it's correct. But take note, alpha is not always 0.05 or zero point 0.01. This could mathematically be computed based from the formula. We have alpha greater than or equal to the variance divided by n times d squared, or n is greater than this ratio, no? Sigma squared divided by d to the power 2 times alpha, where the variance where the variance of number of samples, where the variance, the number of samples, and its difference are predetermined. So we have what we call the Chebyshev's sample size formula. Okay, so where the variance, the number of samples, and its difference are predetermined. So this is predetermined. So this is what they call Chebyshev's sample size formula. Now defining a region of rejection. So the region of rejection is a region of the null sampling distribution. It consists of set of possible values which are so extreme that when the null hypothesis is true, the probability is small, that is equal to alpha, that the sample we observe will yield a value which is among them. Now, collect the data and compute the value of the test statistic. Then after that, collect the data and compute the value of the test statistic. Then state your decision and state your conclusion. Okay, now choose an appropriate statistical test for testing the null hypothesis. So the choice of statistical test for the analysis of your data requires careful and deliberate judgment. So we have here the primary considerations. So the choice of statistical test is dictated by the questions for which the researcher or the research is designed. And the level of distribution and the dispersion of data also suggest the type of statistical test to be used. So secondary considerations, the extent of your knowledge in statistics. So that's another thing. The availability of resources in connection with the computation and interpretation of data. So in fact, there are some who doesn't know how to do the statistics, so they just pay somebody who are expert in this area, and they just pay them to do the work. Okay, so it depends on the resources also, financial resources, for example. Then choice of statistical test. This is designed to help you develop a framework for choosing the correct statistic to test your hypothesis. So it begins with a set of questions you should ask when selecting your test. It is followed by the demonstration of the factors that are important to your consideration when choosing your statistic. So choice of statistical test. So presented below are 4 questions on the next slide. So 4 questions you should ask and answer when trying to determine which statistical procedure is most appropriate to test your hypothesis. So here are the questions, the 4 questions that mentioned in the previous slides. So what are the independent and dependent variables? What is the scale of measurement of the study variables? How many sample groups and or groups are in the design? Have I made the assumptions of the statistical test selected? Okay, so this can help us able to choose the statistical test that we're going to use. So to determine which test should be used in a given circumstance, we need to consider the hypothesis that is being tested, the independent and dependent variables, their scale of measurement, the study design, and the assumption of the test. Then we have what we call variables. So before we can begin to choose our statistical test, we must determine which is the independent and which is the dependent variable in our hypothesis. So our dependent variable is always the phenomenon or behavior that we want to explain or predict. Okay, so that is the dependent variable. So defining independent and dependent variables. So the independent variable represents a predictor or causal variable in the study. In any antecedent consequent relationship, the antecedent is the independent variable and the consequent is the dependent variable. So with a single sample and one dependent variable, the one sample z-test, the one sample t-test, and the chi-square goodness of fit test are the only statistics that can be used. With a single samples, with a single samples and one dependent variable, the one sample z-test, the one sample t-test, and the chi-square goodness of fit test are the only statistics that can be used. So they sometimes ask, but don't you have population data too? So you have two sets of data? Yes and no. The answer here is yes and no. Data have to data have to exist, or else the population parameters are defined. But the researcher does not collect this data; they already exist. So if you are collecting data on one sample and comparing those data to information that has already been gathered and is published, then you are conducting a one sample test using the one sample and or set of data collected in the study. For the chi-square goodness of fit test, you can also compare the sample against chance probabilities. So when we have a single sample and independent and dependent variables measured on all subjects, we typically are testing a hypothesis about the association between two variables. The statistics that we have learned to test hypothesis about association include the following: chi-square test of independence, Spearman's RS, Pearson's R, bivariate regression, and multiple regression. So multiple sample test. Studies that refer to repeated measurements or pair of subjects typically collect at least two sets of scores. Studies that refer to specific subgroups in the population also collect two or more samples of data. So once you have determined that the design uses two or more samples or groups, then you must determine how many samples or groups are in the design. Studies that are limited to two groups use either the chi-square statistic, Mann Witney U, Wilcoson test, independent mean t-test, or the dependent means t-test. So if you have three or more groups in the design, the chi-square statistic, we have Kruskal Wallis H test, Friedman ANNOVA for ranks, one way between groups ANNOVA, and factorial ANNOVA, depending on the nature of the relationship between groups. Some of these tests are designed for dependent or correlated sample or groups and/or groups, and some are designed for sample and/or groups that are completely independent. So dependent groups refer to some type of association or link in the research design between sets of scores. This usually occurs in one of three conditions: repeated measures, link selection, or matching. Repeated measures designs, no, repeated measures designs collect data on subjects using the same measures or measure on at least two occasions. So this often occurs before and after the treatment, or when the same research subjects are exposed to two different experimental conditions. So when subjects are selected into the study because of natural links or associations, we want to analyze the data together. This would occur in studies of parent-infant interactions, romantic partners, siblings, or best friends. In a study of parents and their children, the parents' data should be associated with the son's, not some other child's. Subject matching also produces dependent data. Suppose that an investigator wanted to control for socioeconomic differences in research subjects. She might measure the socioeconomic status and then match on that variable. So the scores on the dependent variables would then be treated as a pair in statistical tests. So all statistical procedures for dependent or correlated groups treat the data as linked. Therefore, it is very important that you correctly identify dependent groups designs. The statistics that can be used for correlated groups are the McNemar test, that is for two samples or times of measurement, Wilcoson T test, two samples, dependent mean T test for two samples, Friedman ANNOVA for ranks, three or more samples, and simple repeated measures ANNOVA for three or more samples. Independent means when there is no subject overlap across groups, we define the group as independent. So tests of gender differences are a good example of independent groups. We cannot be both male and female at the same time. So the groups are completely independent. If you want to determine whether samples are independent or not, ask yourself, can a person be in one group at the same time she she is in another? If the answer is no, so it can't be a remedial education program and a singular classroom at the same time. Can't be a freshman in high school and a sophomore in high school at the same time. So then the groups are independent. Okay, so these are the scenario class that give us an idea what is uh, independent groups or dependent groups. The statistics that can be used for independent groups include chi-square test of independence, two or more groups. So Mann Witney U test for two groups, independent Mann T test, two groups, one way between groups ANNOVA, so three or more groups, and factorial ANNOVA for two or more independent variables. Now, skills measurements. So once we have identified the independent and dependent variables, our next step is to choosing, or the next step in choosing a statistical test is to identify the scale of measurement of the variables. All of the parametric tests that we have learned to date requires an interval or ratio scale of measurement for the dependent variable. So if you're working with a dependent variable that has a nominal or ordinal scale of measurement, then you must choose a non-parametric statistic to test your hypothesis. Okay, so here are the diagram of what type of test that we are going to use. No, depends on the situation. Like for example, for scale data, so we have to say if it's one sample. If yes, then check if there's a dependent variable. If it's okay, then you have to check if known, we have here the mu and this factor. If yes, then you can use z-test. If known only the mu, then one sample t-test. And here in dependent variable, so if your study has independent and dependent variable, so you can use Pearson's R. We can have the bivariate regression, or one sample we have multiple independent and dependent variables, so you have to use multiple regression. Now if you have multiple samples, so you check whether they're independent samples or dependent samples. For independent samples, so you have two options here. Two samples, you use the independent t-test, or for three samples you have one-way ANNOVA or factorial ANNOVA. And for dependent samples, you have also two options here. For two samples, you use the dependent test, or sorry, t-test, dependent t-test. Or if there are three samples, you can use the repeated measures ANNOVA or mixed factorial ANNOVA. Okay, so this is the summary class. You have to check now which of this scenario your study belongs. Then how many samples or groups are in the design? So once you have identified the scale of measurement of the dependent variables, so you want to determine how many samples or groups are in the study design. So design for which one sample test, example z-test, t-test, Pearson and Spearman correlations, chi-square, goodness of fit, are appropriate to collect only one set or sample of data. Okay, so there must be how many sample groups are in the design? There must be at least two sets of scores or two samples for any statistics that examines differences between groups. That is, t-test for dependent means, t-test for independent means, one-way ANNOVA, Friedman ANNOVA chi-square test of independence. Then we have what we call parametric test. So parametric test or parametric statistics are used when our data are measured on interval or ratio scale of measurement, trained to need larger samples. So data should fit a particular distribution, transform the data into that particular distribution. Samples are normally drawn randomly from the population and follows the assumption of normality, meaning the data is normally distributed. For the parametric, okay, so parametric assumptions listed below are the most frequently encountered assumptions for parametric test. So statistical procedures are available for testing this assumption. The Kolmogorov-Smirnov test is used to determine how likely it is that a sample came from a population that is normally distributed. So here are the Levin test is used to test the assumption of equal variances. If we violate test assumptions, the statistics chosen cannot be applied. In this circumstance, we have two options. So we can use a data transformation, or we can choose a non-parametric statistic. If data transformation are selected, then the transformation must correct the violated assumption. If successful, the transformation is applied and the parametric statistic is used for data analysis. Okay, so here are some types of parametric tests. We have the z-test, one-way ANNOVA, one sample t-test, factorial ANNOVA, t-test for dependent means, Pearson's R, t-test for independent means, and Bivariate multiple regression. So these are the types of parametric tests. Okay, so we have a nominal data, so we have to test whether it has one sample and whether it has a dependent variable. So if yes, then we can use the chi-square goodness of fit. Otherwise, you have independent variable and dependent variable. So we have to use the chi-square test of independence. And if there are two samples, so you have to determine if it has independent groups. If yes, then you can use the chi-square test of independence. Otherwise, so it has a dependent group, so we have to use the McNemar test. So the non-parametric test inference procedures which are likely distribution free. So non-parametric statistics are used when our data are measured on a nominal or ordinal scale of measurement. So all other parametric statistics are appropriate when data are measured on an ordinal scale of measurement. Example to this is the sign tests. These are tests designed to draw inferences about medians. Okay, so here are the choices. No? If we have ordinal data, so we have to say if we have one sample and determine if it has dependent variable. So in this case, so we have to use the Spearman's R. Or if it has multiple samples, so we have two options here. So we have to see if it has independent samples. So if there are two samples, so you have to use Mann Witney U. Otherwise, if there are 3 plus samples, so you can use Kruskal Wallis H. And for multiple samples, the other part, if you have dependent samples, so we have to check also if there are 2 samples. So we have to use Wilcoson T. 3 plus samples, so we have to use Friedman ANNOVA by ranks. Alright, so I hope you got the idea, class. This is very rough because you want to cover everything in just one session so that we can proceed later on the details. So types of non-parametric tests, we have the sign test, chi-square statistics, and their modification, that is the McNemar test, are used for nominal data. Wilcoson test, alternative to t-test in the parametric test. And we have the Kruskal Wallis test, alternative to ANNOVA, and Friedman test, alternative to ANNOVA as well. So goodness of fit test. So the goodness of fit test includes Anderson-Darling test statistics, ED, corresponding to p-values, p and likelihood ratio test p-values to assess whether a distribution fits your data. So you can use Anderson-Darling test to examine whether a chosen distribution fits your data well. So use the p-value, p, to determine which distribution fits your data well. So number one, identify the p-value for the distribution you want to evaluate. Then compare the p-value to your alpha level. A commonly used alpha level is 0.05. Then a p-value greater than or equal to alpha suggested that the distribution is a good fit. A p-value less than alpha suggests that the distribution is not a good fit. Okay, so choosing the correct statistical test. So here are the summary. So 5 issues must be considered when choosing statistical test. Scale of measurement, number of samples groups, nature of relationship between groups, number of variables, assumptions of statistical test. So we have here the introduction to multiple and non-linear regression. Okay, so as mentioned earlier, so for hands-on statistical software, so you can use Excel class or other software that can help you in calculating or in performing your statistical uh, test. All right, so thank you and hope you are now ready to conduct your study because one of the project that I ask you here in this course is to conduct your study. Okay, applying all those statistical tests that is mentioned in this lecture. Okay, so thank you very much and hope to see you again next time. So this time class I want you to run through the video and just prepare your question now so that in our next session this time we'll just do the asynchronous. I want you to study those things that mentioned in this video, and then our next session we'll have a synchronous session. All right, so just to give you an overview of what we are going to study in this class, advanced statistics. Once again, thank you very much and see you again later on. Bye.